All right, we're going to look at three-dimensional systems, triple integrals, and we're going to look in things that aren't Cartesian coordinates. So the first thing I'm going to want to do here is I'm going to want to draw our typical XYZ grid here. Let's see if I can get a better grid spacing here. Let's try that. So we'll get our XYZ grid here in green. And so here's our x-axis, here's our y-axis, and here's our z-axis. And what we're going to start with is cylindrical coordinates. So cylindrical coordinate system means any point in space, any point P, is represented by some r dimension, theta, and z. And r and theta are the components of polar coordinates. And so let's get a point in space here. Let's put some point off into space. Here. And so this point P will have r, theta, and z as its components. And what we'll do is we'll look at this in two separate ways. First off, we'll look at the z component, which drops from there. So that's z, the z dimension. And then the r dimension is from the origin to that positional component. And then theta is the angle between the x-axis and the r component, theta. So we're able to talk about then this XYZ, this X, Y, and Z making right angles here. And so this is a y component and this is an x component. Let me turn off the grid here for a second. So we have this point in space. There's a pole that there's a clockwise or counterclockwise rotation on, and you're some distance away from that pole. Then the height comes about. This actually becomes useful. A lot of systems have rotational dynamics that flatten into a plane. Conservation of angular momentum means things that are rotating will flatten into a plane. Our galaxy is a good example of this. If we look at the Milky Way galaxy, it has a disk component and then a stellar halo component. Let me see here. I would love to move that over a bit. Let's see here. There we go. And then it has an internal core. And for galactic dynamics happening out in the halo, the stars can be moving in any direction. And they're randomized in diffuse motion. And so your coordinate system for these stars is going to be something we'll see later on called spherical coordinates. But for things like our sun, which is moving in a clockwise direction around the center, right? Sagittarius A star, which is the black hole at the center of our galaxy. So you can have a coordinate system where you talk about your angle of rotation and your distance away from the galactic center and your height above the disk, or your height in the disk itself. And because of the dynamics of this system, because the angular momentum is moving in one direction, height becomes a very special function, where the dynamics outside coming across. So the polar into cylindrical coordinates happen quite often in some physical systems. And the galaxy is the one that, my research and things have gone around, but there are other components where this would make sense. And so what we want to do is we want to look at how we translate. And so things to know is r will be greater than or equal to 0. We only talk about positive axes to find point P. And theta is between 0 and 2 pi. Z is the same as the Cartesian component. So if we want to think about how we translate, then x is the same as the polar coordinate. X is that r vector times cosine of theta. Y is the r component times sine of theta. And z is equal to z. So there is knowing your r and theta component translating into x, knowing your r and theta component translating into y, and knowing z translates back to z. The r component is x squared plus y squared, and the theta component is the inverse tangent of y over x. So we have ways of moving from rectilinear into cylindrical coordinates across. What we want to do is we want to integrate within this system. We want to be able to integrate within this system. So what we're going to do is we're going to look at a element of volume. So again, I'm going to draw my y-axis and my x-axis and a z-axis. That's a little crooked. There we go. There's my z-axis. So there's my x-axis, my y-axis, and my z-axis. And what I want to do is I want to look at an element extended above the plane. So let's bring an element out here. So we'll look at some volume element. Like such. Let me a little bit extra here. Get these little bit extras off. And so these are curved around their rotation. and get my Z components appropriately. And so we're curved around the rotation. So we have two sectors above each other with a differential in Z. So what we can look at is this individual volume element here, V sub k. And if we look at the component parts of it, this angle difference across the wedge is some change in theta. And the length out to this first line, let me get the angle element near the angle element, so that's some delta theta. And then from here out to this point is a distance r. And this extra segment here is delta r. All right, so we have some r that represents the points. We have some change in theta. And then we have some height, which is our change in z. All right, so from here to here is a change in z. From here to here is a change in theta. From here to here is a change in r. And so if we look at the area component that's being swept out, then that's going to be r, making the times delta r times delta theta. And that will make this length times this length in component pieces. And so the total volume component then for each kth component of these, let's see, so this would be, so my change in volume element for a kth component would be r sub k delta r sub k delta theta sub k delta z sub k. As we multiply the height times the width times the arc length, that makes height, width, length. And we want to make sure this is dimensionally correct, right? Because a volume is dimensionally some length cubed. And so we have dimensions of L, dimensions of L. A change in angle is unitless, and some dimensions in L, or L cubed. So we do have a dimensional correctness within our cylindrical system. So if I have some region in space enclosed, then I can create little volume elements inside of it, and the total volume is the sum of all the volume elements I put apart. So if I have some function that's being integrated over that region in space, and that function is in cylindrical coordinates, then I'm going to take the kth radius times the kth change in height element times the kth change in radius element times the kth theta element. And like we've done continually, if we take the limit as the number of partitions go to infinity, conversely, that's the same as the limit as the partition size goes to 0, right? Or not conversely, identically. If I take my partitions, my little partitions, and make their volume go to 0, then I'm going to need an infinite amount of them to fill the space. And if I try to cram an infinite amount of them into the space without overlapping, then their size is going to need to come down to 0. And so if we take the limit of S sub n, this turns into a triple integral over some region in space D, where our function is times the volume element. Now, I like this notation here because this allows us to express the function in any coordinate system. If we are doing it in Cartesian coordinate systems, then f has to be an f of x, y, and z, and the volume element has to be dx, dy, dz. If we're in cylindrical coordinates, then our function has to be in cylindrical coordinates. So our function, or converted to cylindrical coordinates, so some function of r, theta, and z. And then we'll multiply by r, dz, dr, d theta. And we're able to integrate across. So we have set up a triple integral like we have in Cartesian space. All right, I'm going to pause the video here, and in the next video we're going to figure out how to set up our limits of integration within a triple integral like this in cylindrical coordinates.